Hello and welcome to another presentation on understanding Surds at GCSE. Now I think it's only fair to warn you that we're going to be looking at some really tricky ideas in this particular presentation, but I've got absolutely every confidence in you being able to understand all of these things, and many of these things are certainly going to be making an appearance in the GCSE very soon, if not already. Let's have a look at how we prove that root 2 is an irrational number. Now, I'm sure you've already watched the little presentation on YouTube demonstrating that root 2 is an irrational number, briefly discussing first though the differences between rational and irrational numbers. Now, I prefer a slightly more detailed proof, and I find their way of explaining it quite subtle indeed, and it's a subtle proof anyway, but I'm going to just quickly go over how the argument runs here, just for the sake of clarity. I would like to point out though, I would be amazed if something like this turned up at GCSE, or at A-level for that matter, because you've either seen this proof or you haven't. That said, they are trying to bring in lots more proof into the curriculum, both at GCSE and A-level, so you never know. But this is an example of something called a proof by contradiction. Now, we did see an example of a proof by contradiction when we looked at Euclid's proof that there is no greatest prime number. Briefly just going over the structure of the argument, the way the proof by contradiction works is to assume the opposite of what you're trying to prove, and then to demonstrate that following that line of reasoning will always end up with a contradiction. If you end up with a contradiction from an assumption, then it must mean that your original assumption is false. Now, as we're dealing with something which is either true or not true, therefore you can prove, it's a way of proving a negative really, because you assume the positive's true, demonstrate that it's impossible, and therefore the negative must be true. This is what we're going to do here. So, as an irrational number, no number is not expressible as a fraction a over b, where a and b are whole numbers in their simplest form. We're going to assume that root 2 can be expressed as a rational number. If it can be expressed as a rational number, then it can be written in the form a over b, where a and b have no common factors. It is written in its simplest form. In other words, you can't cancel the fraction down. Now that's a reasonable thing to ask of any rational number. Any rational number can be written as a fraction, and there's no doubt about it, 64 over 20, even though it's not written in its simplest form, the value it represents is a rational number. But surely we can write all rational numbers as a fraction in its simplest form. We can certainly cancel down 64 over 20 into 32 over 10 into 16 over 5, and we've written it in its simplest form. So that takes the same value as that. So it's not an unreasonable thing to ask that a and b can be written with no common factors. Now the reason I'm at pains to point that out is that line where a and b have no common factors is the linchpin of the proof. The proof falls down without it. You need to refer back to it at the end. So what we're going to try and show really in this proof is that a and b have to have some common factors, and therefore root 2 can't be written as a rational number. That is really quite a subtle proof, but that's the way it works. Anyway, so let's get on with it. The algebra in it isn't too difficult. We simply square both sides of the equation, ending up with 2 equals a squared over b squared. Rearrange it so we can see that a squared is double b squared, and if a squared is double a whole number, it must be even itself. Now think about it for a little bit longer and you'll realise any even number which is square, if you square root it, it must be even. To give you a few examples, 16 and 4, 16 square rooted is 4, 16 is obviously square. Let's have another even square number, 64 square root, we get 8, another square number. If you square root an even number, you will get an even number. It's because even times even is even. So, as a is even, let a equal 2p, where p is a natural number. This just demonstrates that a is even, because if it's an even number, it can be written as double something else. So p could be any number, it could be odd as well. This will give us 2 equals 2p in brackets squared over b squared. Square out the brackets carefully and you'll get 2 equals 4p squared over b squared, which easily rearranges into b squared equals 2p squared. Well, what have we shown here? We've shown that b squared is even as well, and this implies that b is even too, just like a was even. So if you really think about it now, we're saying that the top of the fraction, the numerator, and the bottom of the fraction, the denominator, must both be multiples of 2. But that goes against our original assumption that a and b have no common factors, and so we've been kind of caught out trying to write it as a rational number by the fact that every rational number can be written as a fraction in its simplest form. Since you can do that with any rational number, write it as a fraction where the top and the bottom have no common factors, they can't be cancelled down anymore, well, you've shown that root 2 can't be written in that form as a rational number, and hence root 2 must be irrational. Now, by all means, have a good think about how that proof works. I don't think it's obvious in the first few minutes. I actually prefer Euclid's proof that there's no greatest prime in terms of like demonstrating a nice easy contradiction argument, but this one rests on a subtlety in that first line, and that's what you have to remember. Okay, let's move from that very, very tough bit of mathematics into something much more simple and recognisable. Surd manipulation. The rules. Now, I know you will have seen these rules before. I don't want to dwell on this for too much time because I'm sure you will be quite familiar with these ideas. But root a times root b is a square root of ab. Okay, let's take two easy numbers which we can plug in there to demonstrate that root a times root b is root ab. Let's just take root 9 times root 16. Now, root 9 times root 16 is obviously really just 3 times 4, which is 12. Now watch what happens if you do root 9 times root 16 equals root of 9 times 16. 9 times 16 is obviously 144, and the square root of 144 is 12. Can you see that that first rule works? Now you can use exactly the same principle for any one of these rules. I'll always like to demonstrate to the students, look, it works with numbers. It works with any numbers, that's why we're writing it with letters, to show that it works with any number. But it's pretty clear if you use some nice numbers, it demonstrates the rule nicely. You can do the same with root a over root b. I guess you could use let's say something simple like root 36 over root 9. Root 36 over root 9 is really just equal to 2, because root 36 is 3 and root 9 is 3. Sorry, root 36 is 6 and root 9 is 3. So you've got 6 divided by 3, which is 2. And if you were to put that all in a square root, you'd have 36 divided by 9, which is 4, square rooted, which is 2. So it's clear that these things work. Let's have a go at actually using some of these rules. Now, the very first rule we looked at demonstrates how you simplify a surd, and I'm sure you've seen this before. I will go through these answers in a second, but why don't you pause the video and just quickly see if you can simplify those surds. And as I've said, it's by looking for a square factor within the number. So I'll give you a little hint for 27 if you need it, but just think of a square number which goes into 27, and then you can rewrite that as that square number times by something else equals 27. I hope you've had a little go at those, and you should be able to see that root 27 is root 9 times 3. Naturally, we can square root the 9 out of the square root, giving us 3 root 3. Root 75 is root 25 times 3, so that is actually equal to 5 root 3. Root 64, that was a little one in there which I like to throw in there because sometimes people write it as 16 times 4, square root of 16 and write it as 4 root 4. That's not incorrect, it's just not finished yet, because 4 root 4 is really 4 times 2, which is also 8 as well. So I hope you didn't do that. I hope you just thought root 64, well that's 8, that's fine. And yes, you're right, root 64 is not a surd, because it's not irrational. Surd, by the way, just comes from the word absurd. Absurd means irrational. That's essentially where we get the word surd, so I'm told. I hope I'm not misinformed there. Root 80 is root 16 times 5, which is going to be square root of 16, 4 root 5, and root 700 is 10 root 7 for the same reasons. Okay, this should be fairly standard stuff so far, but it rapidly does get difficult, and I think you can see why students are quickly overwhelmed by it. Let's talk about rationalising the denominator, because that's the only other skill really which is currently taught at GCSE with surds. There's no other surd manipulation beyond this at GCSE, or for that matter at A level. There's really not that many tricks to surds, to be honest with you. That said, square roots can easily confuse very quickly. So, rationalising the denominator. Well, we're simply asked to do this because in the old days it wasn't nice to divide by an irrational number. Not when you're using long division and you're doing it without a calculator. It's much better to have a rational number as your denominator, and even if it makes the numerator irrational. Yeah, that's the reason why we're doing it. Students often ask, and it's a good question, why are we doing this? Now, There's other reasons as well why it really helps us, and we're going to see a question at the end where that's the case. Let's just have a look though at how we rationalise a denominator for these. Now, if you think you remember this, and I very much hope you do, have a quick go at those three. If not, go straight on to the next slide. Okay, what we need to do for the first one, if it's a simple one where it's just a square root on its own on the bottom, no other term, we just need to multiply by that square root. So naturally, we can't just multiply the bottom by root 5, we also have to multiply the top by root 5 as well, so that it's the same value, yeah? These are equivalent fractions. We can times a fraction by any number, top and bottom, and we don't change the value of it. That's just, it was for that reason why that proof at the start, we could cancel down those fractions. And if you think about it, what the root 2 proof is showing you is that this fraction can never be finished to be cancelled down. Well, that doesn't make sense for any rational number. All rational numbers can be cancelled down, but root 2 can't, which is why the decimal expansion, by the way, goes on forever. So we've multiplied by root 5 over root 5. Really we're timesing by 1 there, which is fine, that's why the value stays the same. Now root 5 times root 5 according to the rules is simply 5, because it's root 5 squared, which is the square undoes the square root 5, and on top we get 7 root 5. Now it's the bottom two which I quickly wanted to talk about, and I'm not going to talk through every single step, but I am going to give you some ideas. What we're doing here is we're using the difference of two squares to get rid of any square roots. Now the difference of two squares says that if you've got a plus b times a minus b, you end up with a squared minus b squared. Notice that everything is squared there. That means that we get rid of all square roots, and we're just going to use that principle. 2 minus root 3, well, let's multiply by 2 plus root 3 over 2 plus root 3. We're still timesing by 1, so we're not changing the value of it, but what we are doing is making it look different and much nicer because the square root's on the numerator. Now, all you have to do is remember to include the brackets and then multiply these out as if they were sets of brackets. Yeah, I often get students to draw little grids because I'm a big fan of the grid method. If you've seen my first module on why I like multiplication by grids, this is another good reason why I like drawing out grids. So I strongly advise you, in fact, to draw out grids when you do this. Now, if you did draw out a grid for 2 minus root 3 times 2 plus root 3, you'd be getting 4, you'd be getting a minus 2 root 3, and you'd be getting a plus 2 root 3. They will always cancel every single time. You'll always get the first number squared, 2 squared, which is 4, minus the last number squared, and root 3 times root 3 is 3. And so you end up with minus 3 on the end. That will all cancel down to 1. The top will be easy to multiply out, because it would just be 10 plus 5 root 3, and you've rationalised the denominator. Now, the last one I've thrown in, just to show you that no matter how ugly it looks, the denominator can always be rationalised using difference of two squares. Just change the sign in the middle and multiply by that particular bracket over itself. So you're just multiplying by 1. Now, I'd like to move on to something really quite tricky, and this has come up. Please don't think it can't come up at GCSE, because I think it's about to. They're trying to make it more difficult, and they've got you to learn sine, cos and tan exact values. Yeah. Now this is an example, and it's taken from a paper which is currently studied at the end of GCSE but before A level. It's called a qualification called Level 2 Further Maths, but a part of AQA, but it's just a little bit of an extension onto GCSE basically. And they put this particular question in there because they're supposed to know trig values, and all you really need is an understanding of how to rationalise surds. So here's the question, and now I'm going to slowly go through the solution. Really, with the triangle, all we can do, look, if we've got two sides and we've got an angle which is unknown, is use SOHCAHTOA trigonometry. There's no other trick we can use, so I'd certainly be thinking along those lines first. So I can say that tan x equals opposite over adjacent, and that gives me 12 minus 5 root 3 over 4 root 3 minus 5. Now, this comes up obviously on a non-calculator paper, so they look at that and scratch their heads and think, this surely can't be done without a calculator. Well, if you're supposed to know your trig values, actually it can be done without a calculator quite successfully. Looking at that monstrosity on the right hand side of, surds on the top and the bottom of the fraction, you'd be tempted to just kind of throw your pencil down and give up, but there's only one thing we can do with that, and that is rationalise the denominator. It's the only trick we know what to use. That's always what I say to the students in this kind of situation. You know, they have to try things as well sometimes. And if you try this, it's remarkable how nicely it tidies up. If we multiply the numerator out, we get 12 times 4 root 3, which is 48 root 3. We're then going to get minus 5 root 3 times 4 root 3, which is going to be 5 fours are 20, and the root 3 times root 3 becomes 3, and we've still got the minus sign before it, so that's minus 20 times 3. We're then going to do 12 times 5, which is 60, and then we're going to do minus 5 root 3 times 5, which is minus 25 root 3. On the bottom, we're going to have something very, very similar. Multiply it out. I'm sure you can satisfy yourself. Pause the video quickly and check you get the same terms on the denominator. And you should end up with a very, very, very tidy, because the numbers cancel out, we end up with on the numerator 48 root 3 minus 25 root 3. Well, that's like 48x minus 25x. It's just 23x, 23 root 3. And on the bottom, you're going to get 23. That gives you tan x equals root 3. Now, if you remember from the trigonometry module, what is being introduced in 2015, apparently, even in foundation tier, and I find this still astonishing, tan x equals root 3 is a value you're supposed to know. It is, of course, x equals 60. I hope that's clear. It's a lot of hard work, there's no denying it, but I'm going to give you a couple more questions like that in the unit assignment so you can have lots of practice. They're really not too tough, and like I say, there really is only one trick in the book. It's just that the algebra does turn much, much nastier than it often appears at GCSE. But sometimes it does get like this. Okay, I wish you the best of luck with the rest of this module. Bye bye.